Thank you for watching our presentation. I am Jose Rodrigo Sanchez Vicarte, and I will be discussing Opening Pandora's Box, a systematic study of new ways microarchitecture can leak private data. This work is done in collaboration with Pradyumna Shome and Nandeeka Nayak from the University of Illinois at Urbana-Champaign, Carolyn Trippel from Stanford University, Adam Morrison from Tel Aviv University, David Kohlbrenner from the University of Washington, and my advisor, Christopher Fletcher, also from the University of Illinois at Urbana-Champaign. Over the past few years, there's been a huge influx of microarchitectural attacks. The principle behind these attacks is that programs computing on private data naturally interact with microarchitectural optimizations, and these optimizations cause data-dependent hardware resource modulation that can be observed either by a co-resident thread or by observing program runtime. These attacks have exploited several major microarchitectural features, including caches, speculative execution, floating point units, and others. Yet, these optimizations only constitute the tip of the iceberg of what microarchitects have dreamt up over the years to improve performance. Our thesis is that as Moore's law slows down and other avenues for improving performance dry up, microarchitects will resort to more and more exotic microarchitectural optimizations to keep performance up. These optimizations may or may not be implemented today. In any case, they have not been studied from a security perspective. If the past is any indicator of the future, they will have novel, if not devastating, security implications. To better anticipate the security crisis, the goal of this work is to perform a systematic study of the computer architecture literature through a security lens. Our rationale is that when implementing current and future processors, microarchitects will, quite reasonably, look to previously proposed ideas. Specifically, we have two goals. First, to find and study microarchitecture with so-called novel security implications. What we mean by novel is related to our second goal, to develop a conceptual framework for characterizing privacy leakage precisely. Novel here means the optimizations we study are capable of leaking program data that could not be leaked before or with significantly different assumptions. Let me highlight one result of our findings as a motivating example. Everyone is familiar with speculative execution attacks such as Spectre. These attacks are disastrous because they enable the attacker to, in the worst case, leak all of program memory. That is, they create a universal read gadget. As part of our study, we show for the first time how microarchitectural optimizations not related to speculative instruction execution and assuming a realistic attacker can also leak all of program memory. Our attack exploits so-called data-dependent prefetchers, or DMPs. Everyone's familiar with normal stream-based prefetchers, but these are just the tip of the iceberg of proposed prefetchers. DMPs are designed to work for hard-to-predict access patterns like pointer chasing, which stream prefetchers cannot handle. These prefetchers are prime for implementation, if they aren't already implemented today, because they help ascend the memory wall. Let's see how to leak all of program memory with such prefetchers. Consider the indirect memory prefetcher, or IMP, patented by Intel. Similar attacks go through with different DMPs. The goal of this prefetcher is to optimize memory indirections. This common and notoriously difficult access pattern often looks like this. Consider the three arrays we're accessing, allocated in user space. We will be streaming through Z and using the values as offsets into Y. The prefetcher will eventually recognize this access pattern and begin prefetching data by using the stream prefetch values of Z as offsets into Y. Finally, we use the values of Y to offset into X. Once again, the prefetcher recognizes this pattern and begins prefetching entries in X using the values prefetched from Y. Having established the functionality of IMP, let's consider how an attacker can trick it into accessing arbitrary protected memory. Consider a malicious process running inside a sandbox, like eBPF in Linux. First, the attacker will set the value off the end of Z to point to a secret when used as an offset into Y. If the attacker were to directly access Y, offset by this value, the access would land in protected space and fail. This allows the attacker to choose which word of private data it leaks relative to the base address of Y. The adversary then activates the prefetcher by inducing its target access pattern. The prefetcher has no knowledge of the bounds of Z because it operates entirely in the memory system. Therefore, the stream prefetcher overshoots the bounds and reads the values set up by the attacker. Having no knowledge of memory bounds, the prefetcher then uses the setup value to offset into Y. This access mistakenly loads the secret value. The secret value is then used as an offset into X. Here, X is conceptually a region of memory that creates a cache covert channel. The attacker can tell which portions of X are in the cache. Thus, they can infer the value of the secret using a channel like flush and reload. The adversary has, at this point, learned the secret value. It can repeat this process with different targets to learn different secret values. Beyond data memory dependent prefetching, our study found 6 additional optimization classes with novel privacy implications. These include computation simplification, pipeline compression, silent stores, value prediction, instruction reuse, register file compression, and data memory dependent prefetching. They come in different shapes and sizes and are related to multiple topics in computer architecture, from value locality to compressibility to prediction to prefetching. They all have implications that would cause disruption to today's software ecosystem, such as breaking the widely deployed mitigation constant time programming. And, as we showed, they are in the worst case as dangerous as Spectre attacks. For the rest of the talk, I want to discuss the main conceptual contribution of the paper, which is a framework for precisely characterizing privacy leakage. We will use that framework to differentiate the optimizations we study from prior optimizations from a security perspective, and show how to more systematically explore potential attacks. The goal of our framework is to highlight the necessary conditions for a program to leak different function of its input data through a microarchitectural optimization. Yet, at the same time, hide low-level details, such as what hardware resource is modulated to communicate that information and the steps the attacker takes. That is, the model assumes the attacker, the receiver, has a perfect view of hardware resource usage. To give a sense of why this is valuable, consider cache attacks. Over the years, there have been many variants of these attacks, like Pirate Probe and Flush and Reload. Further, different variants modulate a variety of hardware resources, such as cache occupancy, replacement information, or even other components on the CPU, such as the cross-core interconnect. It seems like this space is quite complex. But really, all of these attacks can be summarized from a security perspective very simply. They leak the program data memory access pattern. And it is exactly this information which is relevant to software-based defenses, such as constant time programming and software mitigations against Spectre attacks. Let's now see how the framework operates. We start with a microarchitectural optimization. The first question we ask is whether that optimization modulates a hardware channel as a function of data being operated on by an in-flight instruction. We refer to data which is not being operated on as data at rest, and data which is being operated on as data in use. Next, we refine the analysis to indicate more precisely what is being leaked and when. For example, if data is leaked through an in-flight instruction, which instruction? What operand must the data be passed to? These conditions indicate what program data is unsafe because of the optimization. Finally, we state exactly what function of that operand or operands leak. We will give an example of what these functions look like in the next several slides. It is possible that a microarchitectural optimization modulates a channel as a function of both data at rest and data in use, and thus we will perform this analysis flow twice. We will see a specific example of this in the next few slides. For the rest of the talk, we will use one of the optimizations we study, silent stores, as a running example. Silent stores dynamically skip sending store operations to memory when the value being stored matches the value already in memory. An adversary who can observe whether a store is silent learns information about both the data of the in-flight store and the data already in memory. More precisely, they learn information about data in use. The data operand of the in-flight store becomes unsafe. They also learn data at rest. The data in memory at the store address becomes unsafe. With this view, we can characterize all the optimizations we study. As we discussed earlier, we are interested in what data is safe. For optimizations affecting in-flight instructions, data in use, we are interested in what instruction operands are unsafe. For optimizations affecting data at rest, we are interested in what architectural state is unsafe. For reference, we first characterize leakage relative to a standard commercial server processor, like an Intel Skylake part today. We see the usual suspects, like memory address operands, are unsafe, but a lot of data is still safe. Let's now consider what the world looks like when we implement the optimizations we study. Here, we show the effect of silent stores. This column represents the difference between the baseline and the baseline with silent stores. So many fields don't change, but we see that store data and program memory become unsafe. And safe to unsafe transitions represent novel security implications. We could not leak this value on the baseline, but can now leak it in the presence of this new optimization. The rest of the optimizations we study look similar. The meta takeaway is that, considering the union of all optimizations we study, no data is safe. We now do a deeper dive describing what function of data leaks. Microarchitectural optimizations trigger hardware resource usage changes due to interactions between in-flight dynamic instructions, ISA invisible persistent microarchitectural state, like predictors and caches, and ISA visible persistent architectural state, like the register file and data memory. Consider, for example, silent stores. This optimization can be thought of as having two inputs. One, which relies on state in use, the in-flight store data. Another, which relies on state at rest, the data already in memory. Depending on these two values, silent stores maps to two distinct observable outcomes. The first, when the values match, skips performing the store. The second, when the values do not match, performs the store as usual. Our work introduces a simple notation for writing down these functions called microarchitectural leakage descriptors. For silent stores, it looks like this. Note the two inputs and how the return value is conditioned on whether they match. This mapping allows us to precisely articulate security-related information while hiding other irrelevant information. For example, optimization functionality. Using the MLD, we can easily distinguish between the two observable outcomes. This definition helps us reason systematically about potential attacks. If the attacker controls either input, it can perform a search over multiple replays to leak the other operand. For example, it can set its input to 0 and learn whether the other input was equal to 0, repeat for 1, 2, and so on. The other optimizations we study exhibit similar qualities. Beyond what we discussed so far, the paper provides a detailed discussion of the security implications of each microarchitecture optimization class we study, using the MLD syntax to explain ideas and characterize leakage. Silent stores, the example we discussed, has two inputs, one for the store instruction operand and another for the data memory destination. The inputs to MLDs for different optimizations can be very different. Inputs can cover many combinations of instruction operands, architectural state, and microarchitectural state. The output of silent stores also corresponded to two distinct outcomes, denoting whether the instruction operand equals the value in memory. The silent stores MLD output was a rather simple binary output. Not all optimizations will map to a binary output. Consider register file compression. Because the degree of compressibility depends on the values in the register file, the number of observable outcomes increases accordingly. Let's consider how MLDs can be leveraged during the design process. MLDs can be used by architects to compare optimizations and develop safe variants. Consider dynamic instruction reuse. This optimization memoizes the outputs of instructions based on their inputs. If the same inputs to an instruction are seen, the computation can be skipped. In the first variant of this optimization, presented by the authors as S sub v, operand values are directly used as memoization keys. The MLD for this variant will map to two distinct observable outcomes. These outcomes are conditioned based on the value of the instruction operands. An adversary who can distinguish the two outcomes will learn whether the instruction operand values are the same. That is, the operand values themselves will leak. In two other variants presented by the authors, operand register IDs are instead used as memoization keys. The two observable outcomes, therefore, reveal only whether the operand registers match those of a previous execution. That is, the attacker can only leak control flow by distinguishing the two outcomes. This type of analysis can allow architects to reason about the security implications of an optimization from early in the design process. The MLD can be used at each stage of the design process to ensure the security implications of an optimization are well understood. Furthermore, architects can use this analysis to guide the development of secure variants and mitigations against leakage. Besides MLDs and their applications, the paper also details two proof-of-concept exploits. First, an attack showing how an attacker that can manipulate a single dynamic silent store using ideas similar from previous slides across multiple interactions can break constant time cryptography. Our attack works in a realistic threat model where the attacker can only observe the final execution time of the victim, for example, over a remote connection. Although we studied multiple classes of optimizations, we chose to develop a POC for silent stores because it wasn't clear to us whether an attack on silent stores would even be possible, since out-of-order machines are very good at hiding store latencies. Yet, as we show, we are still able to leak secret keys through once believed to be secure code. Second, a deep dive on how data memory dependent prefetching can leak all of kernel memory when the attacker lives in a kernel sandbox, like eBPF. Wrapping up, should we be worried? Will these optimizations be implemented? There is evidence that many of these optimizations are primed for implementation. IMP, the form of data-dependent prefetching we discussed, has been patented by Intel. Silent stores appears to be partially implemented by Intel between the L2 and L3 caches when writing back all zeros, and is explicitly mentioned in the RISC-V memory model docs. At ISCA in 2017, there was a value prediction competition. And finally, instruction reuse is quite influential and has hundreds of citations. A limited form of several classes have already been found and attacked today. Many of these classes have been patented in some form as well. Finally, considering Moore's law, it stands to reason that other data-dependent optimizations, beyond the ones we studied, are also ripe for implementation. As our findings show, these can, in the worst case, create security disasters of the same severity as Spectre and Meltdown. We hope this paper can serve as a first step for more systematically studying such microarchitecture, so that security considerations can inform the development of secure and performant optimizations moving forward.